this video, we're going to be talking about how to approach energy problems in a few different ways, and then the method that I suggest. And then we're going to use that method to solve two problems. So there's a few different ways to approach energy. There is the network on the system changing the overall energy, and those two are equivalent. There is the conservation of energy, and there are energy bar graphs, sometimes known as LOL diagrams, which you'll see in a minute. So our change in energy is the final minus the initial. So if we go ahead and add the initial velocity to both sides, it basically says that the initial velocity plus the work equals the final energy. So that basically is the conservation of energy, is that the initial energy equals the final energy. Now, in the entire system of everything and the environment, EI will always equal EF. But oftentimes the entire environment isn't the system. So the work is basically just accounting for the work that might be added or subtracted to your specific system. Like, for example, if you're taking a look at this one over here, our system might be the earth, the spring, and the block. And then the environmental things might be like the air and ground and stuff like that surrounding it. So with that being said, all of this is equal to that, and it still holds up the conservation of energy principles. This is the format I like to use because conceptually, taking a look at all the initial energies and then setting that equal to all the final energies is the best way to go from my perspective. And then if there happens to be some energy entering or leaving the system, then you would sort of add or subtract a certain amount of energy using work equals force times distance. Now, if you use something like the LOL diagrams, which you may or may not be familiar with, this is a great way to start off conceptually, where we have all of your initial energies and then all of your final energies. And then this is your system right here, where you can see if stuff is entering or leaving it. So in that case right there, it's a good way to track what kinds of energy you have in the beginning. You can ask yourself, is something moving? Is it off the ground? Is it stretching or compressing anything? And you might have something along the lines of this, where you have some kinetic energy to start off with, and then later on that bar is distributed to gravitational potential energy and elastic energy. Either way, you could sort of set that up into a formula and then say kinetic energy equals the sum of these two at the end. So in the end, all of them are really just about the same. So it's sort of your preference. And as I said before, my preference is this right here, just saying all of the initial energy is equal to final, with the exception of work being done on or by the system. So let's go ahead and clear the screen, and then let's work out these two sample problems. So as I analyze this situation, we have a block that's compressed down 0.3 meters, and then it's going to be released up 0.5 meters in the air, and then we're going to see if it has any velocity after it rises up 0.5 meters, which it may or may not. So as I said before, the approach I like to take is the initial plus the work, and that equals the final energies. So in this case, we're not considering any heat or sound lost to the environment, so we're going to go ahead and drop that work part. So your job is basically to identify what kinds of energy you have in the very beginning. Well, we have a block at rest. It is a little bit off the ground, but if you take your lowest point in the problem, you can basically call that a height of 0 meters. So that's what I'm going to do. So we have no gravitational potential energy because that's our baseline height, but we do have a spring compressed. So we have some elastic potential energy. Now the final position would be right up here. Now that is definitely quite a bit off the ground. So we have some gravitational potential energy. The spring is no longer compressed, so that is not a factor. And we probably have some kinetic energy based on what the question is asking us. So the method to solving this is really all the same. Is we do this as our initial setup, and then we break everything out into their formulas and then plug in all the number values we have to solve for unknown variables. So let's go ahead and do that. So I plugged in all my number values, and with this problem, I had to be careful with one of them. So for the elastic potential energy, I have 1/2 kx squared, k being the spring constant, basically how stiff the spring is, the x value being how much it's compressed or stretched from the equilibrium position, the 0.3 given in the problem, and that's equal to mgh. The h was 0.8 because our baseline height was right here, and it's compressed down 0.3, so then it rose up that 0.3 an additional 0.5, which sums up to 0.8 meters. And then we have 1/2 mv squared. So really just did a little bit of algebra, took the product of these, and then we have 1/2 in front of the v squared. So I subtracted 7.84 from the 9 to get 1.16, multiplied both sides by 2 to get rid of that 1/2, and then square rooted both sides, got a final velocity of 1.52 meters per second. So to recap, we identified all the initial and final types of energies. After that, it's really just expanding them out into their full formula form, plugging in all the number values, and then finding your unknown. Obviously, different problems may have some slightly tricky, intricate parts to them, but that just kind of takes practice. Okay, so let's go ahead and clear the screen and take a look at our second problem. Now for our second problem, we have a spring pushing a 2 kilogram block up a ramp and it slides a distance of 3 meters up the ramp. And then we have an x value, how much the spring is compressed. We have an angle, and we're looking for the k value. So as we did before, we're going to have some initial energy. It doesn't look like we have any work here. We're not going to consider any friction or heat or sound or anything of that sort. So then we just have initial and final. So what kind of initial types of energy do we have? We have something at rest compressed against a spring, so just elastic potential energy. And then at the end, it slides a distance of 3 meters. So we're saying that if that's the maximum distance, it will momentarily come to rest, but it's definitely off the ground. So there's gravitational potential energy. Okay, so that one doesn't end up being too complicated there. So it looks like one thing we need is this though, because this is going to be 1/2 kx squared. I kind of noticed that I do basically have all those things except the k, because it's obviously our unknown variable that we're solving for. And then for mgh, I'm noticing that we have mg, but we don't have the h value. So the h value is right over here. So I want to make sure I draw a little triangle. The triangle is going to look like this, where the hypotenuse is 3, this is 40 degrees, and then we want this h value, so we're going to use sine to use the opposite and hypotenuse side. So the sine of 40 degrees equals the opposite over the hypotenuse side. Multiply both sides by 3. And then our h comes out to 1.93 meters. All right, now that that's taken care of, let's go ahead and plug in our numbers and see what we get for this k. So I plugged in all my number values. The 1/2 times the 0.5 squared basically became my coefficient of 0.125. Took the product of these and then just divided both sides by 0.125, and I got a final k value of 302.64 newtons over meters. So again, this one is same principle as the first one. As I said, here's my preferred method right over here. And the only part for this one that was, I wouldn't call it necessarily very tricky, but something you have to pay attention to, is we want the vertical height from the surface of the Earth. We're not too concerned about that diagonal sliding height, but we did need that as our hypotenuse of the triangle. Other than that, we found our types of energy, expanded them out into their formulas, plug in our numbers, went from there, and then we were able to solve for our final k value. So I hope that was helpful in helping you understand how to set up and solve some energy problems. Thanks for watching and listening.